In this video, I'm going to introduce recursion by looking at a concept of recursion, following this through in the next video by showing a recursive solution that implements a given specification. I'm going to start off this video by looking at a line of individuals in a queue, and here you can see the first person in the queue followed by the second, third and fourth person in the queue. Of course, this queue could be much longer. It could be hundreds of people in the queue. Let's just choose somebody in the 400th position, for example. They would have no way of knowing where they were in the queue if they were to look over the shoulder of the person in front of them, because there would be too many people in front of them and they would have to have a line of sight such that they could count everybody in the queue. Now, clearly, I cannot show 400 people in the queue, so I have simplified matters by saying we have just got these 4 individuals making up the queue. For argument's sake, let's say that the person here cannot see where they are in the queue by looking over the shoulder of those that are in front. Let's say that they've got some kind of obstruction there. Likewise, these two, they cannot see where they are in the queue because they haven't got an appropriate line of sight to everybody in the queue. Now, this person is aware where they are in the queue because they are being served. Consequently, this person knows they are in position 1. To help illustrate a recursive process, what we're going to look at is the fact that this individual is going to ask this one, where are you in the queue? And of course, this one doesn't know. So they will ask this one, where are you in the queue? And of course, they don't know. So they will ask this one, where are you in the queue? Now, fortunately, this individual knows that they're at position 1 in the queue. So this individual tells this one, I'm at position 1. So this one, therefore, realizes they must be at position 2 because they've added 1 to what this individual told them. So they now tell this one, I'm at position 2. This one now knows they're at position 3 because they've added 1 to the number that this individual gave them. This individual now says to this one, I'm at position 3. So this person then adds 1 to that 3 and works out that they are in position 4. Now, if we consider what's happened here, apart from the person at the front of the queue, every person in the queue asks the same question. And that question is, where are you in the queue, to the person in front of them. Each person in the queue adds 1 to the reply. What we can see here is the question has moved in this direction and the reply comes back. And as the reply comes back to each individual adds 1 to that reply and then passes it back. Of course, the process of asking the question and adding 1 to the reply would work if there was 400 people in the queue or more. Here I've just shown there's 4 people in the queue. Otherwise I'd have been spending hours explaining what was going on. But we can extend the queue to many more people. But these 3 here, they are the ones that asked the question, and they are the ones who individually added 1 to the answer they've got. There always, however, has to be a base case. And this individual represents that base. And that is where this individual knows where they are in the queue. So the individual at the front of the queue doesn't have to ask the question and doesn't have to add 1. So this individual behaves differently to these 3, or if there was 399 more people in the queue, differently to those 399. Now this individual asks the question and adds 1 to the reply. This individual asks the same question and adds 1 to the reply. This individual asks the same question and adds 1 to the reply. And essentially, all 3 do the same thing. And of course, if you wish to do the same thing in a programming language, it points to the use of a function. Of course, I'm using an analogy here with the queue. But let's stretch this analogy and realize that what this person is doing is asking the person in front, where are you in the queue? and adding 1 to the reply. This person is doing exactly the same. This person is doing exactly the same. So we can say that there is only really one function here. Now the function I've just described, I would want to be able to use that for all of the positions in this queue. So for example, if I look at this person here, they will ask the question and will add 1 to the reply. Likewise these two. But of course the function would also need to take account of the base case, this individual here. They do not ask the question and they do not add 1 to the reply. So the function must be capable of doing two things. The same things for these three, or the 399 people if the queue was a lot longer, and it also must be capable of doing what is required when the function is implementing the necessary tasks for this individual. So in the case of this queue of 4, these 3 people will want the function to ask the question and arrange for 1 to be added to the reply. Whereas if we use the function for this person, we just want the function to return 1, not ask any questions and not add anything to any value, just return 1. Now this implies that the function will have within the structure of its code an if-then-else selection construct, where one of the paths through the function will just end up returning the one that is required when this individual responds to the question they're asked, and the other bit of the selection construct will respond to the fact that it will have to ask the question and add 1 to the reply for all of these positions in the queue. Let's consider the queue again, and let's say that this individual wants to know where they are in the queue. So a function is written to arrange to find out where this individual is in the queue. Of course, for this person to work out where they are in the queue, they will need to know where this individual is in the queue, and then this individual will add 1 to the reply from this individual here. This function will call a copy of itself to arrange to find out where this individual is in the queue. Of course, this individual doesn't know where they are in the queue because they will need to ask this person here where they are in the queue. So what this function will do, it'll call a copy of itself where this will arrange to ask this individual here, where are you in the queue? Now, of course, they don't know. So what they will have to do is to ask this individual, which means that this function will have to call a copy of itself, where this function now will be asking this individual, where are you in the queue? Now, all of these functions will have been based upon the one function definition that was typed in by the computer programmer. So although it seems a bit odd that this function is being said to be calling itself, i.e. this function here, what we're really saying is that this function has been based upon the type typed in by the computer programmer, and it is calling this function, which is a function based upon the same typing in of the function as this function was. Now, all of the functions shown here will have their own little bit of memory space in which they execute, meaning that this function will have the variables it holds stored in one area of the memory, and this function will have the variable it holds stored in another area of memory. But both of these functions will have been based on the function that was typed in just the once by the computer programmer. Let's now consider this function here, which was called by this one. Now, this function's responsibility is to ask this person, where are you in the queue? Now, because this person is the base case, often called the terminating case, and this individual knows where they are in the queue, they're at the front, so they are in position 1, what this function will do is to return the figure 1. And you can see the 1 is appearing here, and of course that 1 is now going to be returned to this function. Of course, this function will now add 1 to the 1 returned here, and that of course will give 2, and we can see the 2 appearing here. Now, because this function was called by this function here, this 2 will be returned to the function above, as you can see. Now this function has code within it that is responsible for adding 1 to what was returned. And in this case we can see what was returned was 2. So when you add 1 to this 2, what you will end up with is 3. And of course this function was called by this function here, so this 3 will be returned to the function above it, as you can see there. Now this function will now add 1 to what was returned to it. So in other words, to this 3 we add 1, and you can see we get 4. And that 4 is telling this individual, you are in position 4. Now let me just remind you, all of the functions you see here are based upon the same definition typed in by the computer programmer. And if we look at these 3 functions here and look at this one, you can see this has 1 returned to it, whereas this one has 2 returned to it, and this one here has 3 returned to it. Now each of the functions must have had somewhere to which this value of 1 could be returned, this value of 2 could be returned, and this value of 3. And because each of these functions takes up its own memory space, this 1, this 2 and the 3 are not getting mixed up with each other, because this function has its own memory area. Likewise, this function has its own memory area, and this function here has its own memory area. So when I say that this function calls a copy of itself, it does. It calls a copy of the function that's based upon the one function that was typed in by the computer programmer. And each version of the function that will exist is based upon that one function. Now, if we consider these 3 functions again, we will know that they all performed exactly the same processing task of adding 1 to what was returned. So when 1 was added to this, 2 was given. When 1 was added to this, 3 was given. And when 1 was added to this 3, 4 was given. And of course, the 2 that this one got when 1 was added to this would have been stored somewhere appropriate. The 3 that would have been produced by this function would have been stored somewhere appropriate. And likewise, this 4 would have been stored somewhere appropriate. Now, the result of adding 1 to the returned value will have been stored in an appropriate variable that would have been defined by the programmer when they typed in the code. Now, the fact that each of these functions can hold a different value is again pointing out the fact that each of the individual functions will have their own space. So for argument's sake, let's just say that the computer programmer called the variable to which the result of adding 1 was going to be stored, they called it x. So each of these will store the result of adding 1 in x. But that x will be in a different memory area for this function and for this function and for this function here. So us as a human looking at that x may say, well, isn't this x going to get overwritten in some way? Well, the answer is no, because the computer programming language doesn't see the x. What they see is area of memory set aside, and they know that that memory of area for this function is in a different area to this one, is in a different area to this one. If we consider this function, it did not add 1 to anything that was returned to it. And that's because when this function was called, it didn't call on a copy of itself. It knew that all it had to do was return 1 because it found out that this individual here was in position 1. So although all of the functions you're looking at here, all 4 of them, are based upon the same function, that function had within it an if-else selection construct. Now these 3 all performed in exactly the same way. They took the value returned to them and added 1 to it. Whereas this function here didn't have anything returned to it, didn't need to add 1 to it, it just returned 1 to here. Let's consider the description I've just given differently using a different diagrammatic approach. Here you can see the space taken up by a function, and this represents the space set aside in the computer's memory, and we're talking about the fourth person in the queue asking this function to find out where they are in the queue. Now this function has all of the necessary code within it, so what it will do, it will call a copy of itself, and that copy will take up a certain amount of space in the computer's memory, which is different. But this function knows it's got to ask the function again where they are in the queue, so we've got to effectively be asking the person in front of us where you are in the queue. And of course what they have to do is ask the person in front of them where they are in the queue, so we can see the function has been called again. Now at this point there is in effect 4 functions being executed and 4 lots of space set aside. But currently where we are in our execution is with this function. The other functions, their execution has been temporarily suspended. They're waiting for the value to be returned so they can add 1 to it. So this function here is dealing with the base case, the person who's at the front of the queue. So what it will do, it'll take the 1 and it'll return it to this function here. Now this function knows that what it has to do is to add 1 to the value that's just been returned. So to this one it will add 1 and get the value of 2. And of course this 2 is then returned to this function, and this function will do exactly the same as what this function did. It'll add 1 to what was returned to it, but in this case of course we will get 3. And this 3 is now returned to this function, and what this function will do is add 1 to what was returned to give us 4. So the person knows that they are in the 4th position within the queue. Now I must stress that each function is identical in terms of the program statements that are going to be executed. But if you just look at these 3 here, you can see they're all different. And that's because although the function has exactly the same definition in each case, they're set aside their own little bit of memory. So this 1 being here and this 2 being here are returned to the same variable and processed, but they don't interfere with each other because they're in their own area of memory. But we do have the case where a function is calling a copy of itself, which then calls another copy of itself, and it then calls another copy of itself. But each of these copies execute in their own little space. Let's say the queue is much longer. What's going to happen? Well, what we can see happening is we'd have the function here being called by the person much further along in the queue who wants to know where they are. They would then call the same function, which in turn would call the same function, which in turn would call the same function, and this calling of the same function would carry on, as you can see here, till eventually we've no more room on the slide to show how many function calls there would be. But it can go on for much more function calls than I'm showing on this one slide. But while you're looking at this slide, I'd like to ask you a question. What would happen if there was no base case? If we never ever got to a position where the person at the front of the queue knew to return 1? Well, this function here would call a function, which in turn would call a function, which in turn would call the function, which in turn would call the function, and it would never end, would it? So we'd have an infinite number of calls to the same function, and of course the program would crash. Now the reason the program would crash is we would eventually run out of space in the computer's memory, because remember, every function call requires a little bit of space, and if we didn't have a terminating condition, a terminating base case, we would continually be asking for more space for this program to execute. Now this is a problem with recursive programs. You can only go round this particular calling and then calling and calling and calling again so many times, and this is something I'll come back to in a later video. But it also goes on to show that if you wish to have a recursive solution to a problem, you have to identify a base case, one right at the very end that will return something without performing the same calculations that everything else have to do when they were called. Let's consider this diagram that we've seen before. This is where a function calls a function, and we can see the values returning and then the addition of the 1 as appropriate. So we know the function will call a function which will have space set aside for it. This function will now call another function which will have space set aside for it. This function will now call another function which will have space set aside for it. And this function will be the base case in this case, and this 1 will be returned to here. So 1 will be added to that to give 2, and that will be returned to here, and 1 is added to that to give 3, and 3 is returned to here, and 1 is added to this to give 4. So we can see as time goes on, we find ourselves calling the functions, and when the values come back, we add 1, and we eventually get the result that we're after, and the result of 4. But look at it carefully, and you can see this required space, this required space, this required space, and this required space. So even if we consider the fact that we have a base case, we can see we're chewing up space. But because we use a stack to implement function calls, we can have the situation where, if you think about it, once this function has returned the 1 to here, this function is no longer needed. So we can remove the space that this has. When this function has returned the 2 to here, we no longer need it in terms of the space set aside for it. So we can remove that space. So I'm now going to look at another animation that shows that happening. So here we can see we have the function of the individual wishing to know where they are in the queue. And what it will do, it'll call the function that will ask the person in front, where are you in the queue? And this will then result in the function being called again to find out where they're in the queue, which in turn will call the function to find out where the person in front of them in the queue. Now this function is then the base case, so we know that it will return 1 to here. Now the instance the 1 is returned to here, this function is no longer needed. It's carried out what it should have carried out, that's the returning of the 1. So the space that it took up is released by the computer. This 1 now has 1 added to it to give 2, and that 2 is now returned to here. And of course this function is no longer needed because it's carried out its purpose. Consequently, that is removed from the computer's memory. Now this function will add 1 to this 2 to give 3, and that 3 is now given to this function, and of course this function has carried out its purpose, so it is no longer required, so it is removed from the computer's memory. In other words, the space set aside for that is removed, and of course what this function will do is add 1 to give us the value of 4. So what we need to take away from this video and analogy that I've shown you is the fact that a recursive function is one that invokes itself. Space is set aside for each call of the same function. So when a function is invoked, i.e. called, space is set aside and this space is used, and when of course the function carries out its task, that space is released again by the computer. The space is added to and removed from the stack. Now at this point it's important that you have some kind of understanding of what the stack is, and essentially this is when you need space, space is given, and then space is taken away, and the space is stacked on top of each other and removed from the top. Now I'll be coming back to look at how the stack functions, but I would recommend that you maybe do some background reading on the structure, the data structure stack, to have an idea for how the stack actually functions. And in the next slide I'm going to show you a very crude animation of a stack, but I would recommend that you did some more background reading. But of course I'll be coming back to look at the stack later in this playlist on recursion. Let's consider a simple animation for the operation of a stack. And we're dealing with the queue that we've looked at so far in this video, and we're dealing with a queue of 4. Now of course we're looking at the 4th person in the queue, and we're going to call the function because they want to know where they are in the queue. Now when that function is called, space is set aside for the first function call, i.e. the 4th person in the queue is saying, where am I in the queue? Now, of course, we know that this function call, within the code of the function, there'll be another call to the same function, and that function will require its own space. So space is added to the stack, and we now have two separate spaces, this one for the first function call, this one for the second function call. And of course, what will happen now is that this second function will call the function again, so space will be set aside for this function call, as you can see here, space for the third function call. Now it too will call the same function, and space will have to be set aside for that, as you can see here. Now what we're looking at here is space set aside for each of the function calls, and those functions will have space set aside so that they can get the value returned and add 1 to that value. And at the moment we're here, where this is the space for the fourth function call, so the fourth function is now executing and it's interrogating the person that's at the front of the queue. This is the space set aside for the call to the function that is going to be inquiring of the first person in the queue, where are you in the queue? And obviously they're going to return 1. And that 1 is going to be returned to the function that has this space set aside. So the 1 is returned to this space. Consequently, the space here is no longer needed, so that is removed. We're now in the execution of the function responsible for setting aside this space. 1 will be added to the one that's returned to give 2. So 2 is now returned to here. And upon that return, the space set aside for the third function call is no longer needed. So that is removed from the stack. This now has a value that it adds 1 to. That is then returned to here, and this space is no longer needed, so it is removed from the stack. And of course this will now have the value of 1 added to what it received returned from the function, and we can stop at this point. I won't go on to explain what happens to this, but of course it will disappear, won't it? So a stack will behave somewhat like this. You will find there will be a need for space for the function call. If it then calls a function, space is required for that, and then you can see the space required for the third function call, and then space required for the fourth function call. So you can see that the stack is building up rather like putting plates on top of each other. And of course what will happen then, as each function call performs its task, the space is removed from the stack, rather like removing plates from a stack of plates. You remove them from the top, don't you? So you can see that the stack will eventually disappear, and then the stack will be used next time you start calling functions. Check out the supporting website for these videos. In addition, why not follow me on Twitter, as I issue a tweet every time I upload a new video.